Assalamualaikum to Dr. Rohana. So my group would like to present our project, which is the final year project titled Similarity Detection System. As we know, every student must submit a final year project title before starting their project. However, the number of FIP title submission increase every year, making it difficult for lecturer and administrator to manually check whether a title is duplicate or too similar to existing titles. This manual process takes a lot of time and may lead to repeat project topics. Therefore, we propose a similarity detection system that can automatically compare new FIP title with existing titles stored in the database. The main objective of this system is to maintain title originally, reduce duplicate topic, and improve the efficiency of the title approval process. To perform the comparison, the system uses three algorithms. The first is Evenstein distance, which measures similarity based on character difference between two titles. The second is Jaccard similarity, which compares the common words found in the title. The third is the KMP algorithm, which detects matching keywords or phrase efficiently. By combining these three algorithms, the system can provide a more accurate and reliable similarity detection result. Next, I would like to explain the system context design. In this system, students submit their proposed FIP title through the system. The title is then compared with existing titles stored in the FIP database. After the comparison process is complete, the system automatically generates a similarity report. This report helps lecturer and admin determine whether the title is unique, need revision, or is too similar to previous project. As a result, the proposal process becomes faster and more efficient. The system consists of four main modules. First is the title input module, where students submit their proposed title. Second is the text pre-processing module, which converts text into lowercase, remove punctuation, and prepare the title for comparison. Third is the similarity detection module, which uses the three algorithms to compare title. Finally, the report generation module creates a similarity report and display the similarity percentage. There are four main entities involved in the system: student, lecturer, admin, and FIP database. Students submit titles, lecturer review the report, admin manage the system, and database store all existing FIP title used for comparison. In conclusion, this system help automate the title checking process, reduce duplicate project topics, and improve the overall efficiency of FIP title management. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Tanpa dengar Mekana Azmat in Malaysia number is 082198, and I will present about the same distance. So the same distance is a way to measure how similar two strings are. It does this by counting the number of small changes like adding, removing, or replacing one character at a time needed to change one string into the representing distance of the other string. So the first introducing the system algorithm for the final year project title similarity detection case study is because the system will log one student example some FYP titles that are very similar among the titles that already exist in the university database. From the historical methods which we determine the performance analysis and scalability. For the time complexity, I use M to represent the length of the text section for a new title, which is what is also between application. So they have a 38 characters, and I use an M for represent the length of the existing title, which will based on still booking system where they have 33 characters. So for the best case scenario, I use a before M times N. So when the new title that the student enters as a matching the existing title in the database, the nested loop are needed to fill a 2D metric tables where 39 times 34 cell to check for similarity, but the substitution cost variable is always 0 during the comparison. For the average case scenario, as in the real scenario of the above code, the majority of the substring of the nets are identical network response booking, but they are variation in the areas like application and system. So the algorithm will read one character at a time from the input and at each position of I and J, and put the cost of the optimal operation, which is minimum. For the worst case scenario, if the new title does not have any characters in common with existing title, such as comprehensive booking, so this is also the worst case scenario. Despite the condition, new title are still equal to the existing title, J-1 to always win, and substitution cost equal to 1 will continue to be applied. So the system needs to be able to calculate the maximum cost for each FYP cell implemented without performing any step. In the space complexity, the memory space that used by the computer is directly proportional with the size of the 2D array by using the Decker matrix 0n and 0n statement. For our total example, the memory need to allocate space of 39 times 34 equal to 1326 integer cell to store the result of the computational subproblems. So this requirement can actually be used to VO minimum and if the algorithm is modified to store only 2 rows of the active matrix while computing. In data-oriented scalability, the comparison operation not only happens in the university database but also in the entire number of current titles of N. Thus, the Western distance PP function should be called N times for every new title that the student suggests. Overall scalability of the system will be N times M times N.
My name is Siti Iduna Mastura. Today I would like to introduce the jacket similarity. The definition of jacket similarity is a set-based algorithm used to measure the similarity and diversity between two groups of data. The application in this case study A, it assesses the similarity between a new proposed FYP title and an existing database title. It also calculated by dividing the number of overlapping or share words by the total number of the unique words across both titles. For the formulation breakdown,
A and B sets of unique tokenized words from title A and title B. A-B intersection, the count of matching words present in both titles. A-B union, the total sum of unique words combined from both titles. Scoring range 0% completely unique titles with 0 overlapping words. 100% the identical titles with exact word redundancy.
so why we choose jacket similarity? To overcome word order sensitivity, leverage term distance,
The first algorithm highly sensitive to word position. For example, changing web-based student management system to student management system based on web result in a massive edit distance, misidentifying it as completely different. For Jaccard, it fixed and converts title into a set of unique keys and successfully detecting the same idea regardless of sentence structure. For the word level versus character level matching, Leverstein operates at the character level, which is
Structural changes and typos, where Jaccard operates at the word level, tracks core keywords. FYP importance, it is essential for checking if core technical keywords, for example Laravel, IoT and Digistrat, it overlaps with existing database project rather than just checking if the spelling character match. The efficiency with pre-processed text, it works flawlessly after eliminating common stop words like a and the. It focuses entirely on the remaining highly significant technical keywords. It is extremely efficient for short, concise token sets, delivering an accurate overlap percentage score.
Then we have the pseudocode for Jaccard similarity. First, we have the processing and tokenization, which is where the title changed to lowercase and punctuation is eliminated to avoid sensitive issue. So spelling of IoT, which is for the capital I and O, will be changed to IoT, which is lowercase for I and T, will be considered the same. And
the title then will be split into a list of words which are the tokens. Second, the stop words removal, the common words that do not have any technical meaning, will be eliminated. This is important as the algorithm could focus on only the main keywords. Next, the list of words that has been changed to a unique element in set A and set B to eliminate any repeating words in the same title. Then the system will count the number of words that overlap and the total number of unique words that are combined. Lastly, the end score counted and written in the form of decimal between 0.0 to 1.0.
Alright, we move on to the time complexity BO analysis. For the first scenario, we have best case scenario, which is the time complexity is big O times 1. This is happen when one or both of the titles are empty after stop words removal. The system will instantly exit without
any comparison element operation. For average case, big O n plus m, it happens in normal situation where the FYP title has standard length between 5 to 15 words. Time taken to complete the process string splitting and insert the token into hash set. For the worst case, big O n times m. In theory, if a very bad hash collision happen in data structure of hash set operation, dot contains can decline to big O m to big O1. Thus, intersection operation become big O n times m. However, in reality, with a good hash function, it will close to big O n plus m, even with maximum input size.
Lastly, we have Jaccard similarity analysis. The space complexity analysis, which is memory allocation, the additional memory is primarily used to store unique words tokens after the filtering or pre-processing phase. Tokens are stored in two distinct hash set structures, set A and set B. Space complexity rating, big O n plus m, where n and m represent the number of unique words in title A and title B
respectively. Linear growth and system impact. Memory scales linearly based on the total number of unique words being compared. Because FYP titles inherently consist of short text lengths, the actual memory footprint per comparison is exceptionally small, highly lightweight, and will not burden the system execution environment. For data-oriented scalability, real-world challenge, previously analysis covers one-to-one comparison. In reality, university databases store thousands of records. The linear search issue, new title submission requires checking against every single record sequential scan. It demonstrates linear searching scalability. Total system complexity, big O, D times n plus m. D for database size, n or m for unique words per title. The performance bottleneck and solution: risk. System slow down heavily as database records grow. To fix it, optimize using inverted index or min hash to skip irrelevant titles and keep system fast.
Moving on the overview of selected algorithms, to build a highly robust detection engine, our system adopts a multi-layer text machine pipeline by combining three distinct algorithms. First, KMP handles character label access phrase alignment. Second, Jacka similarity process word label token sets. And third, Levenshtein distance use dynamic programming to capture minor character modification. By combining this framework, the system cross-examines proposed title from structural, semantic, and literal perspective to guarantee maximum accuracy. Now let us look at the conceptual design of the Knapp-Morris-Pratt KMP algorithm. KMP is integrated into our system specifically for exact substring matchings. Its main job is to instantly flag verbatim, word-for-word duplication of research methodology or sub-queries. Unlike traditional naive search which completely resets its pointer during a mismatch, KMP pre-calculate pattern characteristic into a longest prefix suffix or LPS table. This allows the research window to jump forward efficiently, skipping unnecessary character comparisons. For the technical specifications, our KMP model is structured into two main functions: compute LPS table to calculate jumps boundaries and KMP search to execute the database scanning loop. Looking at the performance analysis, KMP guarantees excellent efficiency. Its best case time is BOM, while both average and worst case times are tightly bounded at linear BON plus M. This linear time is guaranteed because the text pointer never backtracks. Furthermore, its space complexity is highly efficient at BOM, requiring minimal memory to store the LPS array. In terms of data-oriented scalability, KMP handles expanding university databases exceptionally well. Its linear scalability vastly outperforms naive search quadratic regression. However, KMP is structurally rigid and cannot detect similarity if a student rearranges word orders. Because of this, we deploy KMP as our essential first-line filter. It runs first to instantly clean out literal one-to-one copy-paste title at a very low processing cost because passing more complex passes down the pipeline to Jacka and Levenshtein. To conclude my part of the presentation, the FYP title similarity detection system proved that a multi-layer algorithmic approach is highly effective. KMP rapidly blocks exact word-for-word tick. Jacka similarity captures rearranged concept keywords, and Levenshtein distance ensure that minor character edits or typographical errors cannot bypass the system. This synergy provides excellent data scalability, streamlined approval flow for lectures, and ensure that every approved FYP is truly unique and innovative. That is all from me. Thank you very much.